So let's continue our discussion of molecular orbitals by looking at the molecular orbitals that we form in some example compounds. So for instance, we know that hydrogen is a diatomic species naturally. So we can look at the energy of the molecular orbitals that we can form in our hydrogens and see if that explains why hydrogen likes to form a bond. So how many valence electrons does hydrogen have?
1.
Correct. So if we're looking at our H2 molecule, we can look at our valence electron for one of the hydrogens and then also look at the valence electron for the other hydrogen. And we've talked before about how when we form our molecular orbitals, we look at our phase of our two atomic orbitals that we're combining. So here we have our two orbitals are in the same phase, and as we previously discussed, that means that we're forming a molecular orbital that is a sigma orbital in shape. Here's our axis of rotational symmetry. And we have constructive interference, so we've increased the area that our electrons have to move around in, which lowers the energy of our orbital. So our bonding molecular orbital is then going to be lower in energy than the atomic orbitals that we started with. And that means that we're going to stabilize the molecule if we can move electrons into this orbital. Whenever we form a bonding molecular orbital, remember that we're going to form the anti-bonding if we have the two atomic orbitals that are out of phase with each other. And so we can look at our anti-bonding orbital here. Our region here in the center is out of phase, so it's going to subtract and be destructive interference. So here's our nodal plane, our region of no electron density that shows that we've got our sigma star orbital now. Our rotational symmetry is still there. But now we've formed an anti-bonding molecular orbital. So notice that our atomic orbitals are here, and we've actually raised the energy by forming this anti-bonding interaction. So this is going to destabilize the molecule if we have to put electrons in this orbital. So if we look at the number of electrons that we have for our valence electrons from our hydrogen atoms, we have 1 and 2. So we can put both of those electrons down here in our bonding molecular orbital because we know each orbital can hold 2 electrons. So by moving our electrons from a higher to a lower energy, we have stabilized our molecule, and our molecule is going to want to form this interaction. Now remember that the number of atomic orbitals that we're putting in to combine is going to tell us how many molecular orbitals we're going to create. So 2 atomic orbitals went in to create 2 molecular orbitals. So if we want to determine the bond order for our H2 molecule, we can look at the number of electrons that are in our bonding molecular orbitals and the number of electrons that are in our anti-bonding. So remember our designation. All of our molecular orbitals that do not have a star are bonding, and anything that does have a star is anti-bonding. So how many electrons do you see then in bonding orbitals for our H2 molecule?
2.
Correct. So here's our 2 electrons that are in our molecular orbital. And notice that our anti-bonding orbital is empty. So if we want to figure out the bond order, we take 2 minus 0, and then we're going to divide by 2, and that gives us 1. And we know that hydrogen likes to form a single bond between the 2 atoms, so that fits with what we discussed previously. Now, we can compare this to helium, because we know that helium is diatomic or not.
Not.
Not, correct. So helium naturally does not occur as a diatomic molecule. And if we look at the electrons, we can see that each helium actually has 2 valence electrons. So now we've changed the number of electrons that we're working with. So we're going to have 2 electrons from each of our heliums for a total of 4. And so if we start putting these into our molecular orbitals that we formed, 2 of the electrons can go into the bonding molecular orbital, and 2 of them are going to have to go up into the anti-bonding molecular orbital. So notice that while 2 electrons lowered in energy, the other 2 electrons had to raise in energy. And the amount that we lowered the energy is the same as the amount that we had to raise the energy. So there's no net energy benefit for helium to form a bonding interaction. If we look at the bond order, this is just going to confirm what we just saw. So our bond order, we look at our bonding orbital electrons. So there's 2 of those here. And then I see 2 that are in anti-bonding orbitals. So 2 minus 2 is going to give us 0. So we're going to get a bond order of 0. And helium does not form a bond. Now, if we look at atoms that have valence electrons at the n equals 2 level, our energy diagram starts to get a little more complex. So for our 2s atomic orbitals, we're going to get a similar combination of molecular orbitals as to what we saw at the 1s level. So our 2s in-phase interaction is going to give us the sigma bonding interaction. That's our lowest energy here. And then the next highest energy would be the corresponding sigma star for the out-of-phase interaction for these two atomic orbitals. Now our p electrons can also, their orbitals can form bonding and anti-bonding interactions. And we discussed how the two p orbitals that meet head-on are going to interact to give us another sigma interaction, because we have this rotational symmetry that we've discussed defines our sigma bonds. And whenever we form a sigma, we're going to form a sigma star. So here's our out-of-phase corresponding sigma star interaction. Now if we look at the up and down oriented p orbitals here, then the interaction that these two form is actually going to form a pi bond, because we've introduced a nodal plane and we've lost our rotational symmetry. For every pi bond, we're going to have a pi star bond, and see how we now have two nodal planes, and that's due to the destructive interference in between the two. Our in and out of the plane orientation p orbitals are going to do something similar. We're going to have another pi interaction that's in and out of our paper, and then a corresponding pi star. So when we get to the n equals 2 level, we have more orbitals to work with, and our energy diagram gets a little more complicated. So if we want to look at where our electrons fall in these molecular orbitals for atoms that have n equals 2 valence electrons, then we can look at the rankings of the energies from our sigma, sigma star, and then to our molecular orbitals that form from our p atomic orbitals. So for instance, we can look at O2. So how many valence electrons does an oxygen have?
6.
Correct. So we'll have 6 valence electrons for our first oxygen, 6 valence electrons for our second oxygen. That gives me a total of 12 electrons to work with. And we know electrons like to be at what? High energy or low energy?
Low energy.
Low energy. So we're going to start from the bottom up. So we're going up to 12. We'll start with 2, 4, 6, and then these two orbitals here are at the same energy, so our electrons are going to go 7 and 8 unpaired, and then 9 and 10 we're going to have to come back in and pair them. So these rules are going to follow just like our atomic orbital rules did for electrons. So then our last two electrons are going to go 11 and 12, and we're going to leave those unpaired because that's a lower energy system. So for our O2 molecule, you can see that we would have 2 unpaired electrons. And if we want to look at the bond order, we need to count up all of the electrons in molecular orbitals that are bonding. So 2, 4, 6, and 8. And then we're going to subtract our anti-bonding ones, 2, 3, and 4. And so if we get 8 minus 4, we're going to get 4, divide that by 2. There's that double bond that you guys have seen in our diatomic oxygen molecule. So, here's a question for you. What is the bond order and how many unpaired electrons are there in Cn1-? So, when we're looking at this, the first thing to figure out would be how many valence electrons are we working with. So we've got a carbon. How many valence electrons does carbon have?
4.
How about nitrogen? So nitrogen has 5. And then we're going to have to add an electron because we have a -1 charge. So that gives us 10 electrons to work with in our diagram. So let's start at the bottom and fill up. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So sigma, sigma star, sigma, pi. So how many unpaired electrons does it look like we have?
None.
I see none. So we have 0 unpaired electrons. To determine our bond order, we're going to have our bonding orbital electrons minus our antibonding orbital electrons. Divide the whole thing by 2. So I see 2, 4, 6, and 8 in our bonding. I see 2 in our antibonding. So that's going to give me 6 over 2. That gives me a bond order of 3. And if you were to draw out the Lewis structure for this cyanide ion, you would find that it has a triple bond between the carbon and the nitrogen. Let's stop it.